Hello, I'm Alvin, and this is a brief introduction to Chapel. This presentation borrows from other presentations and also borrows from example code provided in the Chapel installation. Links can be found at the very end of the presentation. So what is Chapel? Chapel is a parallel programming language that supports general parallel programming and aims to make large-scale parallel programming more productive. It aims to be as programmable as Python, while being as fast as Fortran, C, and C++, as scalable as MPI and SHMM, as GPU-ready as CUDA, OpenMP, OpenCL, OpenACC, and others, and as portable as C. On their website, they state that Chapel is productive by being concise and readable, and having consistent concepts to make parallel computing easy to learn. It's also built from the ground to implement parallel algorithms such that the user doesn't need to trade low-level control for convenience. Chapel is also a compiled language that generates machine code that can meet or beat the performance of other languages. Chapel is also scalable, being able to use from laptops to clusters to clouds to supercomputers. As previously stated, it's GPU enabled, and it is also open source. In addition to those features, Chapel is a statically typed language, and it's also interoperable with languages including Fortran, C, and Python. This means that it can support calls between these languages. In terms of parallelism, Chapel programs create new tasks via the begin, co-begin, and co-for-all statements. Tasks are what Chapel use to run in parallel by assigning them to cores or threads on the system. There are two tasking options, with the default being queue threads based on a user-level threading package from Sandia National Labs, or FIFO, first in first out, which is more portable but heavyweight, which uses pthreads. In Chapel, a locale is a resource with a processor to run tasks and having memory to store variables. They are not cores, and a locale is more like the computer containing the cores in memory. A locale can also contain multiple CPUs and GPUs. In this code below, it prints here the ID, which is the current locale running the program, and also num locales, which is the number of locales running the program. So running on my PC would print hello from locale 0, and this program is running on 1 locale. For the features in this language and examples, we can first start with begin. A new parallel task is created by begin. So for the code below, there's begin write line hello and write line goodbye. That means there are two tasks going on in parallel, which are not synchronized, allowing hello to print after goodbye, even though it comes beforehand in the code. Co-begin is similar to begin, but it creates a block of tasks that must complete before the original task continues execution. In the code to the right, you can see a co-begin block with the line write line hi, calling the function say hello, and then two more write lines. And then after the co-begin block, you can see write line see you later. For the different outputs shown below, you can see that hi, hello, greetings, and puny earthling are all printed in different orders, or it's not consistent. However, the one consistency is that see you later is always after those 4 lines, because CodeBegin blocks the code. This only applies to child tasks, not descendant tasks though. This means that if you have a begin statement inside the CodeBegin block, the original task can continue execution before the task called by the begin statement is finished. In addition to sequential for loops, Chapel has parallel for loops built in. You can see the sequential one above for the message in 1 to number messages, right line, hello world. And for all is Chapel's parallel for loop. By default, it creates tasks equal to the number of cores on the processor and splits the iterations evenly between them. So, what are the results? You can see the results of the sequential for loop on the top with the parallel for loop on the bottom. On the top, you can see it goes 1, 2, 3, 4, all the way to 16, which is the number of iterations set by the program. However, for the parallel for loop, the order isn't so straightforward. You see 3, 1, 4, 5, and so on. But you can also realize that 1 always comes before 2, 3 comes before 4, 5 comes before 6, 7 comes before 8, 9 comes before 10, 11 before 12, 13 before 14, and 15 before 16, showing how the tasks are split up between the iterations. In their docs, Chapel states that they do not prevent non-deterministic for all loops from being written. It merely implements the parallelism that the programmer specifies. This means that race conditions can exist in for all loops, and it's up to the programmer to realize them and write their parallel loops accordingly. There's also the function co-for-all, which creates a parallel task per iteration of the loop. Looking at the previous slide, for all message in 1 to number of messages, that may have created 8 tasks. But for co-for-all, it would create 16 tasks. And if the number of messages was increased to say 100, while for all would create 8 tasks still, co-for-all would create 100 tasks. This can be used to create tasks per locale, which is useful for programming in distributed systems with multiple locales. Additionally, in the language Chapel, sort is parallel by default. You can see this code sorts an array of around 134 million elements in 1.1 seconds, around 121 million elements sorted per second. Compared to other sorts, like a simple Python sort that's sequential, which sorts it in 108 seconds, and this parallel merge sort using modified code from Quaz, which was done in 6.8 seconds, which is much faster than the sequential Python code, but still slower than the simple sort code provided in Chapel. For miscellaneous features, there's also a swap function in Chapel. As you can see, you can set A to be the letter A and B to be the letter B, and print A and B, swap the functions, and then print them again. And you can see in the output that the values of A and B have changed without requiring a temp variable. Variables in Chapel are also typed similarly to TypeScript, which uses a variable name, colon, and type. Variables can also be typecasted using a colon, and multiple variables can be declared with the same value or type in a single line. For typecasting, you can see that you can set myString to be the string 1234 and myInt to be an int. You can cast myString into an int natively in the language, and then you can cast the int myInt back into a string. And if you print both, they'll both print 1, 2, 3, 4, 5. In the code on the bottom, you can see that you can cast it to an int, add one, and then cast it back to a string all in the same line. For uses of Chapel, applications of Chapel include CHAMPS, a 3D unstructured computational fluid dynamics framework for aircraft simulation, a coral reef biodiversity analysis, and Chapel Ultra, which is ultralight dark matter simulation. To elaborate on CHAMPS, it was written by Professor Eric Laurendale's students at Polytechnique Montreal. The physics models being solved all require supercomputers to solve unknowns from 10 million up to 1 billion. Existing aerodynamic simulation softwares use Fortran, C, or C++, and all of them use MPI. Being written in Chapel, it was written with up to 10 times less instructions lines compared to similar softwares using other languages. Thank you for listening to my presentation, and here are the links and sources if you'd like to learn more about Chapel or try out the language for yourself. Thank you again.